Hi, Simon here, GM8NYV. I'm going to test these two coils, the original one and my replica, to see if there's any difference in performance. Now then, bearing in mind the replica one I made has a ferrite bead as a core. This is it. And the originals are a dust iron. Now there is a big difference here, but that's all I had at the time. I thought I'd try it, but you'll see what the difference is in the end. Now the way I'm going to measure these, I'm going to put them onto a VNA, nano VNA, get a result of them. But before I do that, I'll just explain, if you connect any test equipment to these, the test leads are going to add capacitance to them. First of all, I put this little capacitor across the pins. It's a 150 PF capacitor, and then I'll use a old-fashioned dip meter to see what the resonant frequency is. I've had this dip meter quite a long time. Originally they were GDOs, grid dip oscillators, because they used a valve and they measured the current in the grid of the valve. But with transistors they're now just called dip meters. Basically, as it put this coil here, which tunes from 3 megs to 8 megs, this actually is supposed to be orange, it's faded with yellow. That's 3 to 8 meg. This is another one here. This is 6.8 megs to 18 megs. We have the green one here, band D, 18 to 47, etc, etc. What the dip meter does, when a resonant circuit comes close to this, it starts to pull energy from the coil. And you can actually detect this in a very small, it's very hard to see, but you get a discernible dip in this meter. Let's see if I can demonstrate. First of all, I'm going to put the capacitor across the main coil. I've got this closely coupled. I'm going to move the dial here around, starting about 6 megahertz ahead. You can see a dip about there, and I'll zoom in on the meter. It's easily go past. If you look at the scale here, it's not very accurate. It's reading about 6.2, 6.3. Such a small scale, you could only get an approximation. Now to see what that oscillates at, I'm going to put a receiver near it. So I've put the wires of the antennas of the radio very close, and I start tuning it across here. You can put your hand near it, it'll change the frequency. So it's not a perfect way of detecting it, but it's a rough idea. And the frequency on the radio is 6725 kilohertz, 6.725 megahertz, which is very similar to the scale. Looks about 6.6 there. Right. I made this little test board, basically. It's actually used for something else, but I just added a valve holder in here to plug the coil in. It's probably got a lot of copper on it, and it probably affects the coil a little, but I've also soldered the capacitor underneath it. So plug this in and I compare that with the dip meter. Now with this next method, I'm going to connect the signal generator up to the small coil on the top here. I've connected the signal generator to this little top coil. Use this little coil here I made attached to another probe, and this probe I'm going to plug into an oscilloscope. So I'm using this signal generator because it's easy to sweep the frequency and display it on the scope here. That's a coil from the scope. If I sweep this over a range between 6 and 7 megahertz, it peaks and then dips again on the scope. It peaks about there, roughly between 6 and 7. It's an analog signal generator, but on my scope here, just give me a digital readout. Peak again, around about 6.435 megahertz there. And I'm going to compare that with my one. So using my homemade coil, looking at the signal generator, I'll sweep this again. You should be able to see on there around about 6.59 megs. That was two easy and relatively straightforward ways of checking the resonant frequency of these coils with a 150 PF capacitor across them. I don't know if you ever noticed when I used this one here, which has the ferrite bead in it, the actual amplitude on the scope was lower than the amplitude of this one, which had the dust iron core in it. It's a dust iron core. Now I'm going to put these onto a VNA and we'll have a look at the a plot, we get a better view of what's going on and why this dust iron core is much better than the ferrite. I've got my nano VNA connected up to a small little coil I made as a test coil. I'll slide over the top of the Denco coils. Now I measured the lead here, it's 50 PF, so that would affect the resonant frequency if I connect it directly onto it. A lot of copper in this and there's a lot of copper in that, so just pull the frequency a little, but just for demonstration purposes to see the difference between that coil and my replica, I will use the VNA. Right, now I've connected the coil over the top of the Denco. This is a plot of the impedance on channel S11, S11. I'm going to connect this up to the laptop and run a program called Nanosaver. It's a lot easier to see and analyze these coils. Nanosaver running on a PC connected up to the VNA. I'm going to set the frequency here and 4 megs and 8 megs. I'll just pop this. This is the impedance. I'll just pop this out. Now by altering the core of the coil, it should shift the frequency. There we go. That is original Denco coil with the iron dust core former. Now we'll try my replica. There we have another peak, not as high. The peak is a lot lower. These numbers are the impedance, parallel resonant circuit, so it has a high impedance at resonance. That's the marker of where the last coil was resonating at. I'll adjust this coil on this one to get roughly the same. You see the height difference is different. What I'm going to do now is swap the cores over, put the dust iron core in my coil and the ferrite bead in the Denco coil. This is an iron dust core, ferrite cores in. You see the peak is much higher than the original. I'm going to have to change the scale to see that. Make the maximum 200. So the peak is a lot higher than the original. Now this is I'm going to try and increase the frequency here. I've got an impedance of about 168 ohms there. Now I'll try the original Denco coil with the ferrite bead. This is a ferrite bead on the original Denco. So we can get it in. This is the original Denco coil with the ferrite bead in, and very low impedance there. Right, these are the graphs I printed out from the VNA. This is the Y4T original with a dust iron core. A nice peak there, it's peaking 126. On this one, it's the same coil, but I put the ferrite bead I made in, and it's only roughly a half. This is a comparison of the replica, my replica Denco coil, my manufactured one. The yellow 4T, this is one with the dust iron in it, and this is my replica with my homemade ferrite bead core. Scales are completely different on here. This is 200 max, this is the impedance. It's about 100 and around about 170. When I put the ferrite core in it, it's 150, so it's a smaller scale. It's around about 80. So again, it's about 2 to 1. It's about half as good a peak. Now there's definitely a difference between using the original dust iron core and my homemade ferrite bead on a stick, basically. This gives a much better peak. Now the difference of the peaks when using this dust iron core and compared to the ferrite beads is due to the fact that the dust iron has a higher Q quality factor. It gives a sharper resonance. Also has a lower permeability. The dust iron is around 4 to 35, the mu value that is, and the ferrite is over 100. So this gives it a more efficient resonance circuit. The dust iron cores are also bound in resin and gives better insulation or isolation between the actual ferrite particles. Therefore, there's less saturation, doesn't get magnetically saturated. So I found a summary table here. It gives a quick comparison. There's a iron powdered core and the ferrite bead core. As a primary use is high Q inductors for the powdered iron core, yet the ferrite bead is noise suppression and it's lossy. So it's really the wrong material for this application. The permeability 4 to 35 for the iron, and of course is very high, is 125 to 5000 for the ferrite bead. The Q factor, the quality factor, is very high in the powdered iron, but very low. There's a lot of losses in the bead. So in contrast, according to this, ferrite beads are intentionally designed to be lossy at higher frequencies to suppress noise, and they are used for to suppress a lot of noise in wiring on circuit boards and things. So really they sort of dampen the oscillations rather than sharpen it to a resonant peak. Iron powdered dusts are manufactured for RF applications, oscillators, filters, etc. Whereas the ferrite are usually used in balance, transformers and chokes. So they're not really suitable for this application. Now then, it's very hard to find iron dust cores online. There's a slug from an old coil. It's also a dust iron threaded. To get some of these, even though that's too wide anyway. Now what I did find is a supplier of the actual iron dust itself, and I thought maybe I could use that to try and make my own. So I may be doing that in the future. Anyway, thanks for watching. I hope you found this interesting, and I'll see you next time.